chapter. You got to stay up on it. All right. Can you guys see that all right? Okay. Matter. You've heard this word before. Okay, why does matter matter? The matter is everything that has any sort of mass and anything that takes up space. All the stuff that makes up all the stuff that is, all that stuff is matter. Okay? It's in everything that you do. It's everything that you have. It's everything that is. Now, in chemistry, that's what we study. We study matter. We study how matter is formed, how matter changes shape, the degree to which that happens, how much of it happens, and all of that. That's what we're going to be looking at throughout the course of this semester. Okay? So what is it? I told you already, as far as a definition, is anything that occupies space and has mass. If something occupies space, it has volume. Okay? Volume is how much space something occupies. Like, for an example, an aluminum can. If you take a look at an aluminum can, you just see what you call metal and what aluminum. But if you actually took a molecular view, if you could zoom in a whole bunch of times on an aluminum can and look down and look at the tiny pieces that made up an aluminum can, what you would see, or if it was a pure aluminum can, is aluminum atoms, all sort of in a sea next to each other, all really close to each other. This is obviously not drawn to scale, but those would be like aluminum atoms, for example. So matter, you're going to see, is comprised of these little pieces we call atoms. Okay. Now, even though this says that even though something appears to be smooth, like an aluminum can, for example, it's actually composed of a bunch of tiny little pieces. If you took this and, say these were balls and they were this big and you had them all spread out, you could see that that's not entirely smooth. You got a lot of hills. You got a lot of bumps all over that surface. But when they're really, really tiny and we're so big and we look back at it, standing so far away from the detail and from the contours of that matter, it looks as if it's smooth, okay, because this stuff is so small. But in actuality, it doesn't have to be. Okay, atoms and molecules. I think I might have talked about this before. I can't remember what I mentioned and what I haven't. But atoms are going to be the most basic unit of matter, the most basic functional unit of matter. Now, there are tiny little pieces that can make up atoms, but those pieces themselves are not independent entities that act a certain, they give any properties to something. They don't define what something is. They are just pieces of a whole. Sort of like your cells. Right? You guys have at least probably had some science class where you've learned about what a cell is. A cell is a functioning unit of life. It's got a nucleus with ribosomes and all those organelles and all that stuff that's inside that cytoplasm. You start taking that stuff out, yes, you can see that each one of those things is separate, but they only make a cell when they all work together. Okay? Sort of like what an atom is to chemistry. An atom is the thing that everything builds upon that is structurally, it's functional. You can't strip it down anymore before things don't work. Okay. Atoms are the tiny particles that make up all matter. And what molecules are going to be is when atoms start to join themselves together. For example, everyone knows the chemical formula for water, right? What is it? H2O. What does that mean? That means for every molecule of water, there's one oxygen atom, and there's two hydrogen atoms stuck to that. Okay? Water is a molecule composed of atoms of hydrogen and oxygen. Okay, that's the difference between molecules and atoms. All right. Now, when we look at matter, we can classify matter into three big categories. Okay, is it a solid, is it a liquid, or a gas? Now, there's some other categories that are too complicated. We're not going to get into plasmas and that kind of stuff, but let's just keep it basic. Solids, liquids, and gases. What is the difference between solids, liquids, and gases? Well, you can come up with your own. I mean, if I asked you, if I had two things and one was a solid, one was a gas, you could point to which one was the gas. But if I had you to define what a gas was, that may be an entirely different situation. You find that a lot about your beliefs, too, and the things that you see and the things that you do every day. You kind of know, and you operate under the system that you know what things are, but yet, have you ever tried to define it? For example, you have a general idea of what right and wrong is. I could give you a situation. I could pick a situation, and everyone in here could say, probably with certainty, that it's either right or it's wrong. There are other situations that are more ambiguous, right? It could be this in certain situations. So if I asked you what your definition of right and wrong could be, we could get into a philosophical argument that would last all day, because it's it's very difficult sometimes to define some of these things. Okay, so realize that these are what solids, liquids, and gases are definitions. They're loose definitions of what matter is when it's under certain circumstances. Okay, for example, what is a solid versus what is a gas? How do you define that? Well, a solid is when molecules or atoms, whatever unit we're dealing with, in matter are close together. There's very little space between them. They're close together. They're moving because everything moves. But they're not moving apart from one another. They're sort of hovering around one another, and they're very close together. Okay, so what does close together mean? Well, that's where it's confusing. You can't really define that because it's everything's relative. This is closer than this, but this is closer than this, and you can keep going. But in general, if something, that's where you can get those in-between phases, like plasma is sort of a liquid solid. It's kind of weird. But anyways, solid is a fixed shape. So if I give you, like, for example, a lump of iron, it's not changing its shape. It's sitting there. The atoms are iron atoms that are all sort of really close together. You cannot compress it. You can't force, within reason anyways, you can't force those atoms together to any significant degree to occupy less space than what they already occupy. You can't cram them together. They're not compressible. And they don't flow. They sort of tumble. You can't just pour, solid chunks of iron that they don't flow. They're very rigid and they're stuck. To flow means atoms will slide past one another. In a lump of solid, they don't slide past one another. They're fixated and vibrating. A liquid, look at its shape. It's indefinite, meaning you don't know. It depends on what container you have, right? If I have the liquid that's in that cup, and say I have the same amount of it. I have a certain volume of water. It's in there. And then I pour it into this container. Now it has a different shape. It's still water, still the same amount of water that I had, but since it can change shape, it's one of the properties that make it a liquid. Now, the molecules in a liquid are a little bit farther apart than what they are in a solid. It's hard to say to what degree sometimes. There's no magic number that once it gets this far apart, automatically it becomes a liquid because there's too many things you have to account for. But a little bit farther apart, they become a liquid, and they start to be able to move a little more freely than what they can move as a solid. Okay? However, they're generally not compressible. Now, it's possible, but for what we're going to talk about, we're going to say liquids are not compressible. Okay, think about like how hydraulics work, or even if when you push on your brake, you have a master cylinder. Sort of, it has brake fluid in it, and whenever you can take physics and learn about all that kind of stuff. But the fact that you can't compress it is good because that's what that space in there. Whenever you exert that cylinder on that fluid pushes down on another cylinder down here. So if you just compress it, all you would do, you wouldn't get anywhere. You would just cram all that liquid together and you wouldn't move anything. So it's not compressible. Does it flow? Sure it does. Okay? A fluid flows. That's where these words they come together. Is it a fluid? Does it flow? Yes, it does. A gas. A gas certainly has an indefinite shape. Okay, but I want you to notice something else. If we had these same two containers and that was filled with hydrogen gas, it's going to take on the shape of its container. If I could pour that hydrogen gas into that bottle, I've still got hydrogen gas. I've still got the same amount of hydrogen gas. Let's say, no, let me pick a different one. If I have hydrogen gas in here, okay, and I bring in this giant container, and I set it right here. It's about that big around, about that tall. And I pour this hydrogen gas into this container, assuming I could make a transfer of all of it. I've still got the same amount of hydrogen gas. Agreed? I've not added or taken away. I've just transferred it. I've got a new shape. The hydrogen gas is now occupying a new shape compared to its original container. What else do you know about that hydrogen gas? What else will it do that the solids and liquids will not do? It'll expand. That's exactly right. So gases have an indefinite shape, right? They take the shape of their container. They also have an indefinite volume. They will expand, for example. That you are confined, in that hydrogen situation, you are confined to the volume of this container. Once you put it in a bigger one, it now has a bigger volume. Okay? So it has an indefinite volume. Can you compress a gas? Yes, you can. That's how an air compressor works. There's a lot of, because a gas is something that is matter where the atoms or molecules are so far apart from one another, there's a ton of empty space between them. So you can minimize that space by compressing those molecules and getting them closer together. Does it flow? Yes, it is a fluid. Gases are fluids. So you could be a real smart aleck next time you go to the doctor. They tell you to drink fluids. You wanted to specify because technically you could suck gas and drink a fluid. Okay? All right. Speaking of sucking gas, anybody ever had any dental work where you got to have the laughing gas? That's good stuff, man. That's good stuff. I remember. And you're thinking. I remember when I was sitting there, I was getting 2 wisdom teeth extracted, and the surgeon was pumping the gas in, and I was sitting there, I was breathing it all, and he's like, "Can you feel anything? You want some more?" And what do you say? No. You never say no. You don't turn it down. So yeah, you better give me some more. And I was sitting there thinking, I remember, because the way they do it is they take the scalpel and they'll cut your gum and they'll lay it open and then they'll snip the roots off before they extract the tooth. Yeah, sounds pleasant. But I remember sitting there because I was semi-conscious when all this was happening. I just couldn't feel anything, I remember thinking consciously to myself, oh man, this would hurt so bad if I could feel this right now. Because he had like those little pliers, like those little snips, and I heard him just snipping those roots off, man. Ah. And then you're thinking, and I also remember sitting there thinking, this is laughing gas, why am I not laughing? And that hit you on the car ride home. I don't know. Because I was sitting in the car, my wife was driving, and I was just, loaded off this stuff, and I was sitting there in the passenger, and then, because it was in Terre Haute, it was over there by Regional Hospital where I had it at. And I was about halfway home, and all of a sudden, that's when it hit you. For no reason, I just started laughing uncontrollably. But I had those, this has nothing to do with anything we're talking about, but I've already started now. I had the gauze in, and it fell out, and I couldn't hardly feel it, So all the blood started pouring out my mouth. And I could not imagine what it would be like for the people that pull up next to you. I'm sitting here, I'm laughing like a maniac, and I got blood just coming out of my mouth, and this people are just sitting here looking, what? Whoa. What is wrong with that guy? Anyways, back on track. All right. So, like I said, what you will see is in your 3 states of matter, when you have a solid, liquid, and a gas, you can see that in a solid, things are closer together. Not only are they closer together, as you will see as the semester unfolds, they are actually organized in a very geometric pattern. They are very sort of like alternate, and they stick together. Like in this case, sort of like what a crystal would be. You can see that they make these. This looks like a little ring with them all stuck together. It's very organized. In a liquid, they're sort of just kind of sloshing past one another. In a gas, they actually can spread completely out from one another. Okay, this would be like ice versus water versus steam. Okay. Which, interestingly enough, is that I don't know if I mentioned this already or not, but water is very, very unique. We'll discuss water at the end of the semester. It's the only one that exists in all 3 phases. It's the only molecule on our planet that exists in all 3 phases in natural form. Nothing else exists as a solid, liquid, and a gas on this planet, okay, except for water. Okay. Now, what's going to be very important out of all of this is this right here, this last statement. Because of the fact that they are organized differently, for example, that ice is a little bit different than water, the liquid water. Okay, this is solid water. Ice is a little bit different than liquid water, which is a little bit different than steam in terms of what you know about them and how they behave. Now, they're still water. You can still get the same types of chemical reactions, but they are very, very different because, for example, a steam burn is going to be much worse than a hot water burn. We'll talk about that why later on in the semester. Okay. There's a whole lot more energy associated with these molecules. They're farther apart from one another, and they're moving around a lot faster. So the properties are going to be a little bit different. The properties, the things that make them them, okay, that they can do. Because of this structure, close together, organized, little less organized, almost to the point of disorganization on this one, the fact that they are like that gives them different properties, and we'll be discussing some of that. Take a look at solids. Now, like I said, they're packed close together. This would be like I don't know if you've ever looked at a little cube of salt, like a grain of salt up close or not. But it's actually a very, very, very organized molecule. It's almost like, what lattice is, right? The stuff people put on the bottom of their decks, and it's got crisscrosses. If you can imagine a cube, a 3-dimensional cube of lattice, all the inside is filled with lattice as well. And every point where those lines intersect, where you have 2 boards that intersect, every cross point would be where an atom is located. and there's sort of some space in between, you know. That would be like what a salt, like this grain of salt would actually look like. You would see alternating sodiums and alternating sodium and chlorine atoms, okay, in this particular arrangement. It's very organized. Okay. If you look at a solid, we see that they're packed very closely together and they're in fixed position. That does not mean they're completely stationary. They are certainly moving. They've got stuff buzzing all around them. We'll talk about electrons pretty soon. They've got electrons buzzing all around them. They're vibrating. If you could look at this right now and look at your desk and look at it really closely, zoom into this level right here and look at the atoms that make this up, you would see that it is moving. Everything is moving. It's just moving so little compared to like this type of movement. This is big movement compared to that little tiny movement. It appears as if it's not moving. Okay? Everything is relative. Everything is moving. There's no such thing as static anything in this universe. Okay? Everything's dynamic. It's constantly in motion. It's the degree of that motion is what we have to consider. Okay? All right, so they are vibrating. Okay, your desk is vibrating right now. You just might not feel it because it may be too small for you to sense. Okay, so because they're so close together is why they're incompressible. Okay? Now, since they can't move around and slide past one another and move out, that's why they don't expand to fill the shape of their container. They're so closely packed together that they're sort of attracted to each other to the point where they don't really move. That's why they maintain a fixed volume. They don't expand or anything like that. Now you do realize that how you go now from a solid, liquid to a gas, it's all about can you spread out those molecules from one another. If you supply enough energy, for example, I don't know if you've ever tried to melt salt, but it's pretty hard to do. It's impossible for you to do. You could do it in a lab with enough pressure and enough temperature. Now you can dissolve it. That's a whole different ballgame. I'm not talking about that. I'm talking about actually physically lighting it and melting it. Okay. If you melted salt, what you would have to do is turn it into a liquid that would, only those atoms present right there. You would have to supply enough energy, like heat energy, for example, where those atoms could absorb enough energy to where they start to get antsy and push apart from one another and spread out until you've got a liquid. And it would take a ton more energy to get them to spread out far enough to turn it into a gas. So that's the only difference between solids, liquids, and gases of the same substance, of like water or salt or whatever. It's the degree to which, how close are these things together, how far apart are they, and obviously the farther apart they have to be, the more energy you're going to have to put into it. Separate them apart from one another. Okay? We've got two types of solids. We've got what's called crystalline solids and amorphous solids. The prefix A means what? I know? Without. So morph means, okay, it could mean change, but generally you think of it because of a change of shape. You think of like metamorphosis and that kind of stuff. So I can see where you got that, but actually morph is in reference to the shape of something. Okay, so amorphous means without shape, without any repeating geometric continuity with what we're talking about here. So notice a crystalline solid, how organized it is, and then take a look at what's called an amorphous solid. It's sort of just all the atoms are sort of lumped together. Okay? There's no repeating geometry that is very evident at that point. Crystalline solids make up what you think of as crystals, salt particles, or gems or stones, like diamonds and that kind of stuff. Okay, part of the reason that some of these things are so valuable has to do with the geometry associated with them, right? I mean, the better the geometry, the more proportioned, like the diamond and the jewel is, the more it's going to be worth. Okay, now you can cut that. I'm not talking about the big sides necessarily, because people can cut that and sort of shape that the way they want it, but at a smaller level, like at this type of level, when you're looking in, how geometrically arranged is it? And, okay. Amorphous solids are like plastic and glass. We probably won't get into like polymerization and like how you make like PVC, polyvinyl chloride. Okay, how do you make polymers? How do you make these types of amorphous solids? Glass is sort of like silicon dioxide, which is like sand, right? And you can sort of melt that down and you can treat it to the point. But what happens is you get this sort of inconsistent, not thoroughly mixed or geometrically organized mixture that you flatten out and let it dry, and then or let it recrystallize. It doesn't really recrystallize; it lets it solidify. and it's sort of an amorphous shape. When you get into polymerizing things, what polymers are, all your plastics, your cellophane, all your saran wrap, these are all called polymers, and what they are sort of like chemical threads that are made. Pantyhose would be like nylon, for example, Teflon that you have on your frying pans. And what they do is they take these chemicals that are organic types of chemicals, and they take little units. It's sort of like, remember those, my daughter still has some of these. They're old, but I don't know what they're called. They're like plastic things, and you can stick them together. No, they're not Tinker Toys. They're like big. You can like make big necklaces out of. Yeah, but they're like those big type of beads or whatever they are. But they got different shapes like barrels and octagons and all kinds of stuff. Anyways, a polymer would be like sticking a bunch of those together. You've got these basic units that you're operating with. Like if you had all the same kind, like you had like the cylinder shape, and you made a whole big string of nothing but the cylinder shape, that would be like a polymer. Okay. So what polymers are you take these chemicals and you stick them all together and you make these long, like microscopic chemical threads is what you make. And then you sort of mix it all together and it gives it strength and durability. And that's why plastic is so useful. Okay? But because it's all mixed together, sort of, you don't get much of an arrangement. You get what's called an amorphous type of solid. Okay, liquids. I discussed those already. You can't really compress them very well. They're not as close together in terms of their molecules as what solids are, but they're still not to the point of being significantly compressible. However, because they can move more freely, they can actually, like in the case of the salt molecule, that one sodium and that one chlorine, they couldn't spin around each other. They couldn't make their way past and sort of just swim around. These guys can. In a liquid, they can sort of wedge their way through and keep mixing things together and go around other things. That's what gives them fluidity. That's what allows them to flow. They don't have enough freedom necessarily to completely escape and just leave like a gas does. And that brings us to gases. They have complete freedom from each other. They're not close to each other at all. They have the ability to expand and leave because there's nothing drawing them close together. There's a lot of empty space between the particles, usually, with a gas, and that's going to become important a little bit later on. You can see this picture here, compressibility. Obviously, you can compress gas. There's a lot of empty space between those molecules. Okay. All right, now, another way to classify matter. We've talked about solids, liquids, and gases. Now, we can take that a step further, okay, knowing all of that. We can also look at it this way. Knowing what matter is, remember matter is anything that has volume, takes up space, made of atoms. Okay? Of all the matter that exists, you can have what's called pure substances, or you can have mixtures. In other words, if you have a container, or you have a sample of something, is it all exactly the same thing present, or is there a mixture of separate things present? That's pretty much it. It's pretty easy. A pure substance, all the samples are made of the same pieces and the same percentages. Take salt, for example. If you pour out sodium chloride on a table and you look at it, you look at all the little pieces, all you're going to see, if you zoom it in, assuming it's a pure sample, is, sodium atoms and chloride ions all alternating with one another to make up this crystalline solid. Okay, that's a pure substance. There's nothing else present. There's no nitrogen involved. There's no phosphorus locked up in there anywhere. All you're looking at is the same thing. Sodium and chloride units all stuck together. That's a pure substance. Okay? Mixtures, however, you can have some other things in there. For example, if you consider salt water. Salt water is not a pure substance because you've got salt molecules, NaCl, that are making up the solid. You've got H2O molecules that are making up that which is dissolving this solid. You put them together and you've got those two things that make up this particular solution. Now, it's a mixture because you had to have mixed two separate things together. Now, don't misunderstand and think that pure water has to be a mixture because you've mixed hydrogen and oxygen together. No, that's not the way it works. If I look in there and I see how everything's organized and all the units that I see are H2O, that means all my oxygen and my hydrogen is present. That's how they've chosen to organize themselves in that sample. So my basic unit that I'm operating with is a water molecule. It's pure. That's all that's present in there. However, if I mix water and salt together, I've got two basic units now. I've got the water molecules, and I've got the salt molecules. They're separate from one another. Okay? That's going to be a mixture. Now realize that if I take a scoop of salt water out of the ocean, and I could somehow count all of the salt that was present and all of the water molecules that were present, and then I go 5 feet down the shoreline, and I take another scoop and I do the same thing, I'm probably not going to count the exact same number of salt and the exact same number of water molecules that I just counted in my other one, right? But what I would see is if I took averages, like in a well-mixed solution, you would see that the averages start to repeat themselves over a period of time. You can sort of see an even distribution. Okay, so we've got pure substances and we've got mixtures. Okay? You can have two different kinds of mixtures. You can have what's called a homogeneous mixture, or you can have a heterogeneous mixture. Okay? Now, hetero means different. Homo means the same. Okay? So in a homogeneous mixture, you've got matter that is mixed together between two things. However, it's sort of like all stirred up and evenly distributed. That's a homogeneous mixture. If you consider the sky, for example, there's a whole lot of stuff up in our atmosphere. There's oxygen, there's nitrogen, there's carbon dioxide, there's even traces of argon. There's ozone. There's a lot of different chemicals that are up there, but they all sort of just swim around in this big sea with each other, and they're all relatively well mixed together. That would be like a homogeneous solution. You really don't, or a homogeneous mixture. You really don't think about the sky like that. You don't think of it as being a mixture, but by definition, that's what it is. It's a bunch of stuff all mixed together, sort of all swirled up nice and neatly. If you look at the ocean, salt water, you will see the red and the white represent oxygen and hydrogen, respectively. Those are water molecules. The blue and the green represent sodium and chlorine, which are going to make up salt. Okay? You can see that there's a lot of salt dissolved in the ocean, but it's sort of uniform. If you look at the ocean as a whole, it's pretty well distributed. It's all sort of stirred out. It's a homogeneous mixture. Everything's spread out. Now, if you consider, however, heterogeneous mixtures, you're going to find, like if I take a sample, I'm going to see something like, whoop, I didn't see it on that one. For example, if you have vegetable oil and water, if you have a cup of water and you pour vegetable oil in it, what happens? They separate. That is not a homogeneous mixture. They are not evenly distributed. You've got two distinct layers. You can even see where they separate from one another. Okay, they are not evenly, those molecules are not evenly distributed. That's a heterogeneous mixture. Okay? Concrete. Concrete has a lot of stuff in it. You know, it's got rocks in it, rocks of different size, pebbles, calcium carbonate. Now you can even get, you know, fiberglass, little pieces of fiberglass in your concrete. That is definitely, there's no way that you're going to get a concrete truck that's completely distributed all that very well. You know, you let concrete settle for a minute, you know, you can even see the components of it, one sample of it settle apart. Okay. Okay. I got Cold Stone Creamery on my mind. You ever been there? Is that not awesome, man? I just mix, whatever, just throw it all in there. Just mix it all up. I was thinking about those types of mixtures. Those are definitely heterogeneous mixtures. Okay. Tell that to them next time they're fixing it for you. You know you're preparing me a heterogeneous mixture. They're going to say, yeah. Mix it all up for you. All right. Now, when you have substances that cannot be broken down any further, for example, if I gave you a lump of sodium, I don't know if you've ever seen sodium metal. Sodium metal is extremely soft. You can cut it with a butter knife. Okay? If I gave you pure sodium, I would get in a lot of trouble, first of all, and you held it in your hand, and I told you to divide that into a simpler form of matter, you couldn't. Because what you have is a big collection of nothing but sodium atoms. You cannot divide that any further. You can pull out like protons and electrons, but then that's not matter. You've got to have atoms to have matter. You can't simplify that any further. However, if I gave you a sample of water, and I told you to simplify that, take it down and reduce that to another form of matter, could you do it? Anybody know how? It's real simple. You can do it at home. Huh? If you boil it, technically all you're going to be doing is turning liquid water into gaseous water. So you've not changed water. Well, by definition, a liquid is melted. That's what it is. Take a battery, and you run an electrical current through water, you can cause water to separate into hydrogen and oxygen. Okay? It's actually pretty simple to do. You could take 2 test tubes, or you can't. There's more steps to it, but if you can see what I mean by this, you're not going to be able to tell by looking just at home what's what, which is hydrogen, which is oxygen. But you could take a test tube, and you could turn it upside down in water, and if you don't believe me, you can test this. Turn it upside down in water, get a wire. You got to make a circuit to go through. You hook on the top of the battery, take a wire, pass it through the water, come up the other end, bring it to the other side of the battery. So you got a complete circuit. Let that electricity run through that water, and then keep that test tube turned upside down in the water, and then leave it up, pull it up whenever you're done, let it run for a while off that battery. You probably see some bubbles start coming up through there. That's the gases that are being released and escaping, going up into your test tube. When you pull it up, as long as you keep it this way, okay, upside down, the gases are less dense, right? They're just going to float up. If you turn it upside down, and the top's here, all the gases are going to leave. You leave it this way, they're trapped in there. Take a match and light it, see if it doesn't ignite. It'll just poof a little bit. It's not going to like blow up a big fireball or nothing. But you can, hydrogen gas and oxygen gas are both flammable, okay? So you could do that and see if I'm lying to you or not. Just don't blame me if you burn your house down. Do it for the kid. Then you teach them that, then they're doing it while you're not there, and then they're just setting up little bombs everywhere. All right. So if you can't break something down any more than what it already is broken down, like that piece of sodium, for example, you have an element. You have elemental sodium. An element can't be broken down any farther into a different type of matter. Okay? That's what you see on your periodic table, the periodic table of elements. What those represent are all the different types of atoms that we know of. We call them elements because those things, most of them, there's some of them I will point out later that do not exist in nature. Some of those elements that you're looking at are man-made. Okay? They exist for fractions of a second, but because they've existed, they get credit for having existed. Okay? Some of them are naturally occurring, and they exist just the way they are. You can't break them down any farther. Okay? That's what an element is by definition. So that's what the periodic table of elements actually is. It tells you all those different types of atoms that can't be broken down any farther. Okay, however, in real life, most of what we're always going to see are going to be the result of the combination of elements. We're going to see compounds. Okay, a compound is just that. You're compounding. You're taking two things and bringing it together. Okay? So anything that is made of more than one type of element is a compound. For example, oxygen is not a compound. Oxygen is O2. It is made of 2 oxygen atoms stuck together. So it is a what? When two or more atoms stick together, what do we call it? It's a molecule. It's not a compound, though, because there's only one type of element present, oxygen. CO2 is a molecule, but it's also a compound because it's 2 different elements that have come together to make this molecule. Okay? So it's a subtle difference there. Now, what's interesting here is this last check mark. It says properties of the compound are not related to the properties of the elements that compose it. For example, is water flammable? Is oxygen? Is hydrogen? Okay, you see my point. The constituents, the things that make up this compound, are going to have different properties, almost certainly. They're going to have different properties than when they come together and they make some combination of the two. It's just like you and your parents, right? Your mom's one way, your dad's one way. There's a lot of things about you. I mean, you're not going to be in a genetic identical and to every possible degree exactly like one of your parents. Okay, and some of you may be more like one than the other. But you see what I mean. You're going to be something unique that is a result of the combination of those two. You're going to have different properties. You're going to behave differently. Okay, now depending on what table you look at, what periodic table you look at, I'm going to just go with this. There's about 116 known elements. 91 are found in nature, and the rest of them are going to be man-made. Now, you may see tables that have 106, 109. There may be some with 116. It just depends. That's not something worth debating. I mean, it's not a big deal. It depends on what they've decided to include on their table. If you take a look at your periodic table in your book, however, you can see that like with 110, 11, 12, 14, 16 at the very bottom of the big chunk of the table, some of them don't even have names. They've not been named. Others have really weird names based upon people and other things. It just depends. If you look at some tables, you may see, I don't know the one that I put on the web for you to print off, but sometimes you'll see like hollow letters, things that are not colored in all the way, and they're just like outlines of the letters that make up these symbols. Those generally, that kind of representation generally means that those are man-made elements. They only existed for fractions of a second. Okay? We're going to talk about all these numbers on this periodic table and what they all mean. Okay, when we talk about the abundance of a certain element, I'm talking about how much of it by percentage comprises nature. You'll find that oxygen, for example, is probably the most abundant element in nature. We have a lot of it in our body. We have a lot of it in our atmosphere. We have a lot of it in everything that's alive in its free form. Now, there's a lot of carbon too, but carbon is actually locked up in other things, right? Locked up in carbohydrates and other molecules. I'm talking about free oxygen. That's just pure oxygen, O2, floating around. There's a lot of it out there, and there's a lot of it inside of us in our body at any given time and other living organisms. So you end up with oxygen as being probably the most abundant element by mass on the Earth. Okay, the amount of free oxygen weighs more than the amount of free anything else that we actually have on our planet. Now, it's going to vary in different parts of the environment, obviously. I don't know if anybody mountain climbs or even goes on trips to high altitude places, but we'll talk about this a little bit later when we get to gas laws, but why it's harder to breathe, for example, the higher up you go, why your ears pop, why do all these things happen? And it has to do a lot with the fact that there's less oxygen up there. We can discuss the physiological factors a little bit later, but there's a higher concentration of oxygen the farther down you go, as opposed to the higher up you go. So obviously you're going to be able to measure more oxygen down here than you are at the top of Mount Everest. Okay. A compound, like I said, is when two or more different types of elements come together. But it's more than that. It's not that they just happen to hit each other and hook up and stay floating around together. That's not the way it actually works. To become a true compound, you've got to have always the same proportion of each type of element when they combine. For example, in water, you know that there's one oxygen for every two hydrogens. That's what water is. You can't just have water, you can't just say everything that has hydrogens and oxygens coming together makes water, because H2O2 is also just hydrogen and water, but that's hydrogen peroxide. Drink a big jug of that and see if it does the same thing as water. Okay? It doesn't. All right, so for example, water is 89% oxygen and 11% hydrogen. There's billions of known compounds that exist out there, because as you can imagine, it's not just about what you make, it's not just about what atoms you use, it's about how many of them that you have and what ratio you have of one to the other. So that gives you limitless possibilities in terms of creating different types of chemicals. You can have organic or inorganic. This is inorganic chemistry. We're not going to get into organic chemistry. Organic chemistry centers around one atom, carbon. Carbon is so versatile and can do so many things, and you'll learn why when we talk about electrons and electron structures. It's so versatile and can do so many things, it can form so many more compounds than everything else. We have to have a whole branch of chemistry devoted just to that study. It's called organic chemistry. Okay? We're sticking with inorganic, things that are not like that. Okay? They could involve carbon, certainly, but they don't fall into that group of what we would call organic chemistry. Okay, carbohydrates, for example. You've heard this probably in your other classes. How carbohydrates got their name? Take a look at, what's the formula for glucose? Anybody know? Okay, C6H12O6, right? If you're pretending like that was a fraction, for example, or whatever, you know how you reduce to lowest terms? Reduce that to lowest terms, and what do you got? CH2O, right? Carbohydrate for the water. Okay? What a carbohydrate is, by chemical definition, is any compound whose formula can be reduced to CH2O. Okay? That's how they got their name. When they were first discovered, people thought that we're going to learn a little bit later in this semester about types of chemicals called hydrates. They're things that have little tails of water attached to them. Water molecules kind of mix in with them and attach to them. This looked like the formula for something that just contained a whole bunch of carbon atoms with water molecules stuck around that carbon atom. So obviously now we know that's very wrong. But at first when they were discovered, they were named as carbo for carbon and hydrates because it looked like a hydrated carbon atom. That's not the case, but that's where they get their name. So glucose, all these sugars out there, the ribose, deoxyribose, glucose, fructose, lactose, all these things are all carbohydrates because they share that in common. Okay, we've already discussed this, but do realize that we have what's called subatomic particles, things that are smaller and even below the atom. And we have to know these. Every chapter 2 of every science class that you'll ever take is always that one chemistry chapter, which you go through and no one really ever understands. You just memorize 8 valence electrons. You remember what valence electrons are, and you remember the word carbohydrate somewhere, and you remember some dot with rings around it, like a sodium atom and a chlorine atom, and that's all you ever get out of that chemistry chapter. Huh? And then that's it for that chapter. Okay? We got to go way past that. So we're going to look at these subatomic particles, where they are, what do they mean, how do they affect the behavior of this atom. Okay. So we said that the atoms make up molecules, and if you have a compound, the smallest piece, like water for example is a compound, the smallest functional piece that still retains the properties of water is H2O, which is a molecule. Okay, that's what this is saying here. Okay, so before we get into those particles, let's check our classification scheme so far that we've got for matter. We've got pure matter, we've got pure substances and mixtures. For example, let's take a look at pure substances. That means they are pure. They don't have anything else mixed in with them. We can break down pure substances even further into elements and compounds. Say this is copper. You got copper wire. If you were looking at it, you would see nothing but pure copper atoms sitting around here, nothing else present. So it's certainly a pure substance. There's nothing else in there with it. How you would also classify it is it's an element. It can't be broken down in any simpler form. You can't break it down any farther than this and still be something on the periodic table. Compounds. Take these lumps of sugar. The only repeating unit that you see over and over in that sample is, let's say, C6H12O6. Okay? Let's say it was crystallized glucose. It looks like sucrose, and it's not going to be that formula, but let's just pretend that it was glucose. You would only see glucose molecules. Now, is it an element? No, because you've got carbon, hydrogen, and oxygen that theoretically could be separated from that molecule. So this is not an element. This is an element. Can't be separated anymore. But however, both of these are still pure because the functional units, the things that are present that make that sample, are individual units of glucose, for example, and individual atoms of copper here. So this is a compound. This is an element, but both of them are pure substances. Okay? Look at a mixture. Mixture is you're mixing stuff together, obviously. Now, when you mix two things together, it can be homogeneous or it can be heterogeneous. Okay? You can have, like pop, for example, that's made of sugar, water, and carbon dioxide, all sort of mixed around, pretty homogeneous, well distributed. Or you can have something that looks like this, some sort of oil on top of water that's completely separated. That's a heterogeneous mixture. Any questions about that? Okay, I'm moving on. Physical properties versus chemical properties. Someone said a while ago, we were talking about how do I break down water, and someone said boil it. And someone else said melt it, I think. And those are perfectly reasonable thoughts to have. The difference is very subtle. It is about whether or not you are changing water into something else besides water. If whatever you are doing, something happens, and you still have water as a result of it, that was only a physical change. You have not chemically changed anything. only, for example, the state of the matter. You went from a liquid to a gas. If, on the other hand, you pass an electric current through water, and now you have separated water into hydrogen and oxygen, that is not just a physical change anymore. You've done a chemical reaction. You've separated atoms. You've now created two things that behave very differently than water. That is a chemical change. Okay, so you need to understand the difference between physical and chemical changes. Okay? So let's take a look. Look at iron. Some physical properties of iron. It's a silvery solid at room temperature. It tastes sort of metallic, if you've ever tasted metal before. It's got a metallic taste. It's got a smooth texture for the most part. If you can ever reach that temperature, 1,538 degrees Celsius, good luck. Tell me how that turns out. If you could ever reach that temperature, you could melt iron. Okay? You could do it in an industrial setting, certainly, but in your kitchen, probably not. If you can get it ever to 4,428 degrees Celsius, you can vaporize iron. You can turn it into a gas. Okay? That's a pretty high temperature. The density of iron. Remember, density is a ratio of mass to volume. It does not change when you change the sample size. As long as you have the same thing, it doesn't matter how big of a piece of it you have, it will always have the same density. Because as you increase its mass, its volume increases proportionally. Okay? That's what density is. The density of iron is 7.87 grams per cubic centimeter. That's a physical property. It's still iron. If you melt iron, all that you've done is changed it from solid iron to liquid iron. It's still iron. If you boil it, you've taken it from liquid iron to gaseous iron. Still iron. Okay, it's a physical change. Iron can be magnetized. It's still iron, so it's still a physical change. It can conduct electricity. No, not as well as other metals. All this is physical properties that can be resulted from physical, that can contribute to physical changes. Okay? Physical properties, physical changes. Ductility. Anybody know what that word means? Yes, sort of both. The ability to be made into a conducive wire is what ductility means. Okay? You can sort of draw it out into wires. Its ductility and its thermal conductivity, how well it transmits heat from one place to another, are about average for a metal. That's a physical property of iron. It takes that much heat. We'll explain that a little bit later, but joules are a unit of heat. Okay, how you can measure it. You know how you can measure like BTUs and that kind of stuff. We use the whole. BTU stands for what? You know. You heard of BTUs, like for kerosene heaters and that kind of stuff. British thermal units. Leave it to us outside the metric system. Okay. Joules, however, is an SI unit. That is, we have to convert BTUs to. Joules is a unit of heat energy. It requires that many joules, for example, to raise the temperature of 1 gram of iron 1 degree Celsius. Still, it's iron. Okay, now that I've driven that home, let's consider that with chemical changes. Chemical properties, I guess, of iron that could be involved in chemical changes. Iron is easily oxidized. In other words, easily reacts with oxygen. Okay? That's what rust is. So if you don't believe me that it's easily oxidized, then you don't believe in rust. And to be that, you have to be a fool to not believe in rust. You can take iron atoms, and when they react with oxygen, they form a compound known as iron oxide. Generally, it's iron 3 oxide, but it doesn't have to be. We'll talk about that later. Like Fe2O3, for example. A couple iron atoms, 3 oxygen atoms can form this little unit that we call iron oxide. That's what rust is. Okay? When you put iron in hydrochloric acid, it bubbles and the iron disappears. It doesn't really disappear. You fail to see it anymore, but it's there. Because what has happened is the iron that was all compressed together into a solid, the hydrogen from the acid reacts with it and pulls it apart. Okay? Now, the hydrogen from the gas, the hydrogen from the acid turns into a gas, and those are all the bubbles. That's why it's all bubbling up and while it's all leaving. But the iron, all that the acid really did was pulled apart the iron from that lump and spread it all out through the solution. So, like for example, hydrochloric acid is HCl. It's a hydrogen atom and a chlorine atom stuck together. We call it hydrochloric acid. What makes it dangerous is when you put it in with something, they easily separate from one another. And the hydrogen is very reactive, and it'll go and it'll bond with stuff. It'll create chemical reactions. So what ends up happening is that hydrogen separates, and the Cl that's left over, it'll go and bond with that iron. And it'll start pulling that iron apart from itself till it spreads all out, to where there's so much space between the atoms you can see in that space, and it looks like nothing's there. Okay? When in fact, there's a whole lot of those atoms still floating around in there. The hydrogen, now that it's free, instead of combining, now it has to combine. It's reactive. It wants to combine with something. It ends up combining with the other hydrogens that pulled off from the Cls. Those hydrogens end up coming together and make hydrogen gas that then escapes, and that's why it's all bubbling. Okay? You'll be able to tell me all about that later, because by the time we're done with this semester, I'll be able to ask you what happens when you mix two things together. Are you going to have a reaction? What things are going to form, and how much of it's going to form? Okay? You'll be able to answer all these. Baby steps, though. All right. Iron, for example, is more reactive than silver, but less reactive than magnesium. One of the things about gold, for example, and titanium and platinum, why these are important metals and why they're worth so much, is because they are very unreactive. They don't react with things very well. If you don't believe me, next time we're in lab, bring in a piece of solid gold. Give it to me and let me drop it in concentrated acid. I will show you that if it's pure gold, you will not get a reaction. You can wipe it off with water, and you've still got your piece of jewelry. However, if there's any doubt that you have impurities in that jewelry, you might not want to do this, because you're going to lose some mass. Anything that's not pure gold and sort of other things mixed in, like any brass that's mixed in with it to make it like 14 or 10 karat or whatever, that mass will, whatever those atoms are, will react, and you'll lose some mass from that jewelry. So you might not want to take me up on it, but realize that it is theoretically true. If you have pure gold, will not react with hydrochloric acid, for example. That's why they don't turn colors. Your rings don't, unless they're cheap and they're not made with those actual precious metals. Instead, they're made with more reactive metals like coppers and brass and that kind of stuff. Those tend to tarnish, right? Even silver will tarnish. That's a chemical reaction. A lot of people, if you have silver jewelry, old silver jewelry, or silver candlesticks or something like that, candlestick holders, they will tarnish over time. And what people do is, because they don't understand the chemistry behind it, right? And that's fair enough. Not everybody does. Is go out and try to scrub it down. You'll buy some abrasive cleaner. You'll buy something from the store and try to clean that tarnish off. But there's a much easier way where you don't lose silver atoms. Because if you try to clean anything and rub it on there, what you are doing in theory is trying to take off what you see there, that spot, that tarnished spot. Realize there are silver atoms locked up in that tarnish. And what you don't want to do, if at all possible, is remove all of that, because you are removing silver atoms with it. And that's why it's valuable, is because those silver atoms are there. So you know what you can do. This is why it's nice to know chemistry sometimes. What you can do is get an aluminum pie pan, okay, and create a baking soda solution. Dissolve some baking soda in water, put it in an aluminum pie pan. Get one of those bigger pie pans if it's like not a flat piece of jewelry, but like something big like a candlestick holder or whatever. And put this piece of jewelry in there. And what you will do is facilitate a reaction, because what that tarnish is actually sulfides, usually, like a silver sulfide. There is sulfur gas, a little bit, always traveling around in the air. Okay? And what tends to happen is when silver bonds with that sulfur, it forms these silver sulfides, which is that tarnish that you see. So instead of removing that, why don't you do a chemical reaction that will extract that sulfur and leave that silver? That way you've lost nothing, right? You get rid of the tarnish and you leave all your silver that was there. And then as years go by, you're not losing silver. So if you do this, what will happen is you can create an aqueous solution in this pan, and you're actually going to use aluminum the aluminum from the pie pans to react as atoms. That's solid, that's elemental aluminum in that pie pan. You will cause, some of those aluminum atoms can go through that solution. They can, you have to set it there for a while, but they can react with the sulfur. They can pull the sulfur out, because aluminum is actually more reactive than silver, in which case it will bond with the sulfur more than the silver wants to bond with the sulfur. It'll pull that sulfur off, leaving the silver behind. Now when sulfur forms, though, realize that because there's some water that you dissolved all this in, Hydrogen can react with sulfur. There's hydrogen in water and that kind of stuff. Hydrogen sulfide can escape, and that's that rotten egg smell, like rotten meat, nasty smell that you think of when you think of sulfur. That smell that you smell, that's actually hydrogen sulfide, H2S. Because sulfur is pretty reactive, so it'll bond with hydrogen, atmospheric and liquid, whatever medium it's in. The reason for the baking soda was to neutralize that smell. The baking soda then can react with any hydrogen sulfide that's produced and neutralize it so that there's not that big stink coming out of it, and voila, there you go. Little MacGyver skill there. Okay? Now give me a paper clip and a chocolate bar and I'll show you how to make a bomb. Not really, but okay. To bring it home, I'm sure that we got some smokers in here because, you know, everyone's so concerned about their health. Yep, I'm picking on you. That's fine. I'm going to pick on you. As if you haven't heard it yet, right? And if you already haven't put your dukes up and get in defense, everybody gets mad when you persecute the smokers. Now, if you consider this, for example, here's a butane lighter. Butane is a 4-carbon compound. It's made of 4 carbons and 6 hydrogens. Okay? Its formula is C4H6. What you do when you burn it is release the energy that's trapped up in those bonds. Okay? That's what happens when you burn something. You actually react it with oxygen. There's plenty of, the reason this lighter works is because of all this oxygen that's out here in the environment. You try to light a lighter in outer space, it won't work. Okay? You can't light it. You can't light a match on the moon. You can't smoke a cigarette on the moon, much to your dismay. So if you plan on going to the moon, keep that in mind. Now, the reason this flint is here is to create enough frictional energy to supply to the immediate, right around the top of this lighter are oxygen atoms. What you want to do is get these butane molecules to react with these oxygen molecules. There's actually 2 oxygens stuck together, so it's a molecule, okay, an oxygen molecule, O2. You want to somehow get them to come together and shuffle up their letters, come together and make a new compound out of this. The problem is you can't really do that just by pushing this little black thing, because if you do, they're just going to all fly past one another and probably never have enough energy to ram into each other to cause a reaction to occur. So that's why you strike. Notice how fast all this happens, right? You strike this and you see energy released in the form of light. There's a lot of heat energy. And there's enough heat energy that you see it in the form of light. You call that a flame. Okay? That's enough to immediately supply all of those molecules right around that area with enough energy to when they collide, they can actually form a chemical reaction when that occurs. So oxygen combines with butane, and you will get 2 products. Okay? You will get carbon dioxide and water. Those are the 2 products of almost all combustion reactions. We combust things. We take carbons from glucose molecules in our diet. We breathe in oxygen. What we breathe out is carbon dioxide and water vapor. Our automobile does the same thing. It combusts fuel, octane, heptane, and other types of carbon compounds that are in that fuel. And as a result, some of which what comes out of our tailpipe is carbon dioxide and water vapor, along with a bunch of other crap. Okay? Now, if you just push this trigger without striking the flint, what you would see is that this liquid butane would just evaporate. It would all leave. Is that a physical or a chemical change? That's a physical change. You're going from liquid butane to gaseous butane. Okay? If you heat water, you raise its temperature, but it's still water. You evaporate butane. You dissolve sugar in water. When you dissolve sugar in water, you still got sugar and water. You've just spread them out from one another. If you heated it up, as you will see in one of the labs we're going to do, if we do salt water and you heat it up, you can evaporate away the water and leave behind the salt. It is still there. It's not gone. Sometimes when you mix things together, it's gone, but that's the case when it's not. That would just be a physical change. Okay? Now, what if you strike that flint and start a reaction going whereby this butane leaves, and as it's passing out, it starts to react with oxygens, and as a result, they start converting into carbon dioxide and water molecules. What kind of change is that? Certainly a chemical change. Okay? Rust is a chemical change. It's combining with oxygen. Burning butane means reacting it with oxygen. That's what burning means. Silver combining with sulfur to make tarnish. That's a chemical change. Now, how can you separate mixtures? If I give you a mixture of something, like salt and water, that's an easy one. How do you separate salt water into its components, into salt and water? I already told you. What do? You can boil it and evaporate it. They've been doing it for thousands of years over by the Dead Sea. That's how they get their salt. It's the saltiest, inland body of water that exists. You get it out, you get a bucket of it, spread it out into a large bowl with a whole lot of surface area, not one that's deep, but one that's very shallow. Spread it all out, and that water will evaporate very quickly, and you got a lot of salt left behind. Okay? That's an easy way to separate two things. You can also filter something, right? You make coffee, don't you? You have to keep those grounds separate from the liquid that comes through. You're separating a mixture, because there for a while what you have is a mixture of water and coffee grounds, well, steamed coffee grounds, whatever else might be in there. You've got to separate the components because you only want some of them. You don't want all of them. So certainly filtration is one way to separate, especially states of matter, like a solid and a liquid, for example. There's another thing on here called chromatography, which we're not going to get into and we won't do an example of, but realize it has to do with the desire for certain things to bond to a certain surface more than other things. Does that make sense? If I have two compounds, and I know what they are, but they're all mixed together, and I want to extract one of them, I'll find, like, say, a piece of paper. You can do just paper chromatography. And I can stick that paper in there, and what will happen is there will be an attraction by one of those molecules to that strip that I can keep doing that, and I'm actually physically extracting out some of those molecules, leaving the other ones behind. That was sort of a rough explanation of what chromatography would be. Volatility, that's just evaporation. A little bit different than just regular evaporation that we talked about a while ago, because in the case of evaporating a saltwater solution, you had to put in a lot of heat and let it do it itself. Volatility has more to do with like gas and water. Like if you had a mixture of octane and water in a little cup, it wouldn't take very long for that octane to all just quickly evaporate. It's very volatile. You don't have to heat it up. Just let it sit there for a minute and it'll all evaporate away, leaving behind the water. Density. You can use the density of two things to your advantage. Because, like, especially for those of you in MLT, you use centrifugation, right, to separate the sediments and that kind of thing. What do you know about the things that you're separating in terms of their location? What can you tell me about that? That's exactly right. The more dense something is, the farther in the bottom of the tube it's going to be. That's a good way to separate things, if you know that two things are different density. Now, I've left this one because it's obviously the most interesting. Distillation. Distillation is how you can separate things based upon differences in their boiling point. Everything boils at a different temperature. Okay? If you have two molecules, to turn them into a gas, it occurs at different temperatures. No two things have the exact same what's called boiling point to turn them into a gas. Now, there's a little bit of history, right, of our country that's tied to the process of distillation. It's certainly easy to do. For me in the chemistry lab, it's really easy to do because I have the equipment that you see up here, but you could also makeshift it and do it in your own home. Why, for example, is distillation associated with the production of alcoholic beverages? Well, if you consider, first of all, how you make alcoholic beverages. Now, to make them fancy, you got to do a lot more, but let's just say you're hardcore and you're a moonshiner, and that's pretty much what you want to drink is just gross, pure ethanol. Okay? How would you go about making this? Well, consider this. Let's look at first this example that I have up here, and then I'll explain how you could sort of translate that into something at home. Not that I'm encouraging this. I'm just saying, here's the science behind it. Okay? Let's say I want to take this starting solution. What I need is something that will produce ethanol. Well, what's really nice is, anybody ever bake fresh bread, make their own bread? It smells like alcohol for a while. It does. If you take yeast and you mix in your sugar and your flour and let that react, or if you ever had Amish bread and you got to start from somebody and you kind of let it set and then you open it up and smell it, it smells like alcohol because there is alcohol in that. There's ethanol, the kind that you drink. Okay? Because what yeast will do is bring in compounds eating, like sugar, for example. Okay? Bring in sugar. Yeast will digest it, and when they do, they excrete two things. They pee out ethanol, okay, and they also release gas in the form of carbon dioxide. Now, we have capitalized on that because we trap this yeast pee, so to speak. We trap this ethanol and use it in a big part of our industry, right? Because what you can do is take this sample right here in its bare form. Okay, if you were moonshining, this is how those guys got busted. They didn't get busted because of their apparatus. They didn't get busted because of the stuff they were making. It was easiest to track these moonshiners because of all the sugar that they bought. Okay? If you buy sugar and make a sugar solution, dissolve it in water, you got to heat it up. We'll have a Bunsen burner. They didn't. Okay? But take a Bunsen burner, heat up the sugar water and dissolve it, and then take some yeast, just like from the store. People didn't really get busted on the yeast so much because everybody made their own bread anyway, right? But you had to use a whole lot of sugar to make this happen a lot of times by how much they were making. Because sugar, once it's consumed, it's gone. But you can reuse yeast because as long as it's alive, it'll keep working, right? So you don't have to buy as much of that. Take this yeast. You can even go to the store now and buy that dried yeast, put it in there into your sugar solution, and let them start living. You'll start seeing little bubbles pop up as they are making this stuff. The bubbles are carbon dioxide that they are releasing. So what you can do is let this react, okay? Don't seal it all up yet. Just leave it in this vial, for example. Have a sugar water solution with some yeast, and they're going to start eating that yeast. And when they do, they're going to start producing carbon dioxide and ethanol. Now, for us, we don't really want to trap that carbon dioxide. It's no use to us, so we can just let it set and ferment, right? Let it set and ferment, let that carbon dioxide leave, and let those yeast continue to produce some of that ethanol, that ethyl alcohol. Then, when we think the reaction's done, we could filter. And we could separate out those yeast, the big chunks of yeast if there's anything left, or if there's anything else that's in there we don't want. Just run a filter process, and you can have a solution now that's like a sugar water probably solution with some yeast and some ethanol in it. Now your task at this point is to separate out that ethanol because no one wants to drink all that other stuff. And plus, there's probably not a whole lot of ethanol in there at this point to be of any benefit to you. There's just a little bit. Okay? So what do you want to do? You want to utilize the fact that water and ethanol boil at two different temperatures. You can turn ethanol into a gas much easier than you can turn water into a gas. So think about this. Let's seal this up. Let's crank up the heat. Let's monitor the temperature. You actually would probably have a thermometer in here, about right here, to watch the temperature. Watch the temperature so that it doesn't get to the boiling point of water, which is what? In Celsius, do you know? It's Fahrenheit. What's Celsius? 0 is freezing for so. 100. Okay, keep going. You'll get it. 100 degrees Celsius. You don't want to get it to 100 degrees Celsius because that means water will boil and turn into a gas. Instead, you want it down lower. Okay, anywhere from, I don't know, I forget now. It's anywhere somewhere between 70 and 90 degrees Celsius. When you control the temperature and leave it at 70 to 90 degrees Celsius, water will not vaporize. Alcohol will. So any alcohol trapped down here in this solution will start to rise up out of that solution as a gas. It's going to rise up, and it's going to travel right through here. And guess what I've got going right here? I've got a water jacket. I run cold water. There's a tube, and then around that is another tube that is running cold water through it. Why? What will it do to that gas? It'll cool it down, turn it back into a liquid. So you condense that alcohol as it's boiled off. You condense it, and you collect it. You've got ethanol out here to the side. Now what you then would want to do is repeat this, take this, redo it again until you've tried to purify it as much as you can. Okay? Now the sugar source can vary. You'll see that, vodka's potatoes for the sugar source. Let's see, rum is molasses. And there's a lot of other stuff out there that you can check on. But as far as like these old timers and how they worked it, they didn't have this kind of stuff. So instead, you could get just a regular fire and a jug to react this in, and they would actually have a balloon above this. Why would they have a balloon? Anybody know? Yeah, they don't need the gas, but what it will do is tell them how much gas was produced so they can monitor the reaction. They can get an idea as to whether the balloon is just kind of there or is it popped straight up. If it's popped straight up, expanded a little bit, there's been a lot of carbon dioxide produced, we can move on to the next step. I can monitor. It's a way for me to watch what's going on here. Okay, so then they would have a bunch of copper coils. They would have copper tubing all coiled up, packed in ice. Okay, really cold. It's the same thing as what a condenser tube would do. And then you could collect it on the end. Okay, and you could see that this probably wouldn't taste all that great. It's just pure ethanol. Now, with distillations, with distilleries like Jack Daniel's Distillery, and all that kind of stuff, they've elaborated, obviously, this process, mass-produced it. The flavoring process, additives can be added, but also the source and the things that you bring in, like strawberries, watermelons, whatever it is that you use for your sugar base, is going to affect the flavor as well. So all those things taken into consideration. Okay.